you can probably start sharing your
Yep, I'll do
slide.
that. Just give me half a
Yeah,
second.
yeah. So I welcome Sarang Gopalakrishnan, and Sarang is faculty at City University of New York, and he received his PhD in physics from University of Illinois at Urbana-Champaign. And his research interests are theoretical quantum many bodies physics, dynamics far from equilibrium, chaos and pattern formation, and interaction between light and collective states of matter. Welcome, Sarang. Over to you.
Thank you. Can you hear me okay?
Yes.
Okay, great. Right, so thanks very much for having me here. I kind of apologize for not having anything directly to say about space-time duality, but hopefully some of the things I talk about today, will provoke some interesting applications of space-time duality in the future. At least that's what I hope will happen. Okay, so I'm going to talk about a couple of works that we've recently been doing on measurement-induced phase transitions in the presence of symmetries. And so the first case I'm going to look at is the case where the system has time translation symmetry, and the second case is the case with charge conservation, or U1 symmetry. Okay, before I get to either of these cases, let me just do a quick overview of measurement-induced criticality, because this might also be a good setup for Mateo's talk tomorrow, for example, or Tarun's talk tomorrow. So the basic phenomenon we always care about in this kind of context is you take a bunch of degrees of freedom, you say some of them are the system and some of them are the environment. You can divide your time evolution into operations that take place entirely within the system and operations that straddle the system environment boundary. And so after this, you have two choices as to what to do next. You can either look at the environment, in which case you've performed a generalized measurement on the system, and that leaves the system in a pure state, or you can say you don't know what the environment's doing, and so you've got to trace over it because you're ignorance, and that corresponds to an evolution that takes a pure state to a mixed state. In both these cases, you can now forget about the explicit modeling of the environment, and so if you took the sort of environment attitude, then what you have is a quantum channel. And if you took the measurement perspective, what you have is a quantum trajectory. And of course, any quantum channel can be written in Krauss form as a sum over quantum trajectories. And so, these things have to obey the trace preservation rule and have to be completely positive, but otherwise they're pretty flexible. One thing I do want to emphasize is that there's a lot of degeneracy in terms of the specific Krauss maps that give rise to a specified quantum channel. So the quantum channel is much more. A quantum channel can be decomposed in a number of different ways in terms of trajectories, and these are all physically different, because if you were actually performing these projective measurements, you'd be getting the outcomes. You wouldn't be tracing over them, and then you'd be doing different physics in the two cases. So individual trajectories contain more information than the channel does. Okay, and so in particular, if you look at expectation values of operators, it doesn't really matter whether you decompose the channel into trajectories or you just implement the quantum channel, because if you take an expectation value in terms of the trajectories in terms of Krauss decomposition, you can see that by plugging in what an individual trajectory is, you can just perform the sum over the ends explicitly, and that just ends up giving you being the same as evaluating the operator in the quantum channel. On the other hand, if you have anything that's not an expectation value, even something that's, for example, a quantum uncertainty, that cares very much about the way you decompose the channel into trajectories, because it's a nonlinear function of the trajectories. And so the nonlinear functions of trajectories contain a bunch of information that you wouldn't see just by looking at the quantum channel or at the master equation. And so this is the information that we're after when we talk about measurement-induced phase transitions. And so here's a quick example that I'll sketch. So the purity in an individual trajectory is pretty obviously a nonlinear function because it's, the trace the square of the density matrix, right? So, and so you can ask, if you start out with, some particular initial state that's mixed, and you perform measurements, do the measurements, demix the state or not? And so, for example, if you take this Bell state and you measure the first spin of the z basis, then you basically collapse the superpositions, and you end up with just a simple product state, and that's saying the measurements acquired information about the states of the system. On the other hand, if you measure the first spin in the x basis, you don't do anything. You started out with a rank 2 density matrix, and if you just work through the math, you end up afterwards with still a rank 2 density matrix. And so these are the two things that can happen when you perform a measurement on a mixed state. You can either get information, you can not get information. Information might be hidden from the observable you're measuring. And so the question that we can ask now is, suppose you perform a bunch of measurements on a complicated system. Is that going to lead to the system purifying, or isn't it? And the somewhat surprising answer that was figured out a couple of years ago now is that, in fact, there are two phases. There's a phase where an initially mixed state purifies under the action of measurements, and there's a phase where purification doesn't happen. And so the way to think about the more surprising phase where purification doesn't happen is basically that the scrambling action of the unitary gates acting on the system effectively serves to hide information from subsequent measurements. So the information gets encoded in very non-local degrees of freedom, and local measurements can't get at it. And so in some sense, the system acts as a quantum error correcting code. And so in this phase where a mixed state is not purifying, it remains mixed for an exponentially long time in system size, and so in effect it sort of stays it stays mixed forever. So it has some subspace that remains invariant under the action of measurements. And an equivalent formulation to think about this is that you can say, does an initial state get highly entangled, or does it remain low entanglement under this action of unitary gates and projective measurements? And so these are sort of the same question, because you can take half the system and ask what's its entanglement entropy, and that's like asking what's the purity of that half of the system. And so these are somewhat similar perspectives. The purification perspective has the advantage that it doesn't rely on any spatial structure. So, for example, if you talk about mean field models, there is no entanglement transition because there's no local entanglement structure, but there is still the possibility of a purification transition. Okay, and so a lot is known right now about how these purification transitions work in systems in random circuits in certain solvable limits. And in these random circuits, what the transition looks like is a percolation transition. And so that's nice, but it raises a couple of awkward questions. The first is, how important is percolation in general to the physics of these transitions? Do you need randomness in order to have the transition in the first place? Also, since everything is inherently random in time, you can ask, well, is there any notion of spectral chaos, which there would be, for example, in chaotic equilibrium systems? Is there anything like ETH level statistics you can talk about in this context? And the second question you could ask is, how robust are these transitions if you add
Sarang, we totally lost you for the last 4 or 5 minutes, maybe.
Okay, that's unfortunate. Okay, so can you hear me okay now?
Yes, yes. At least I can.
Can you see this application? Its slides, can you see? Right?
Yeah, I can see.
Is my
Okay.
is my screen share showing?
It is
Okay,
showing.
I'll scroll back to when you lost me. So was I audible here?
Yeah, I think pretty much this slide.
Yeah, this slide.
Okay, fine. So let me start again, and so please stop me if I become inaudible again.
Thanks, Sarang. Thank you.
Yeah, no worries. I don't use WebEx very much, and so I don't know what happened, but I assume it's some kind of weird connectivity issue.
No, Sarang, I don't think it was your problem. But maybe from the next slide would be fine.
Okay, fine. So I guess just as a 2-second summary of what happened in the slide, I said that these two possibilities. The first is that measurements acquire information about the system, and they increase the purity by acquiring information. The other possibility is that measurements learn nothing about the system, and so mixed state remains mixed, right? And so the key point is that both of these things can happen in random circuits with random measurements, and there's a phase transition between the two possibilities, and the phase transition is described in certain solvable limits by a percolation transition. Okay, and it's also an entanglement transition between highly entangled subsystems and weakly entangled subsystems. Okay. And so this raises some natural questions. One of them is, how important is the percolation picture? And in particular, how important is spatiotemporal randomness to get these transitions? The second question is there a way to think about them in a spectral way, which is very helpful for concepts like eigenstate thermalization, level statistics, and so on. But if the system is random in time, you can't really talk about eigenvalues of anything. So that would be a nice thing to fix. And the other question is, suppose you add structure. Suppose you make it not a random circuit, but something more structured. Does the measurement transition remain? In free fermion models, it's known that it doesn't remain. In fact, you don't have a volume law phase at all because your dynamics is not scrambling enough to hide information from the measurements. And so you can ask, well, suppose I don't go all the way to free fermion. Suppose you put in like a small number of conservation laws. What does that do to the transition? Okay, and so I'm going to address these questions in turn pretty briefly. Can you guys still hear me?
Yes.
Fine. So the first case I'm going to consider is the case where you have time translation invariance. So because measurement outcomes are random, if you just make the measurements time translation invariant, that's not going to be enough. What you also need to do is you need to post-select on having the same measurement outcome over and over again in order to get a time translation invariant evolution operator that's unitary plus projective. And so there's a particularly nice case where this happens, and this is for quantum channels that are in some sense close to the identity. And so when the quantum channel is close to the identity, the channel consists of two parts. It's got unitary dynamics. You know what unitary dynamics close to the identity looks like? It looks like Hamiltonian evolution, right? But you also have to think about what the jump operators do when they're close to the identity, when the evolution is close to the identity. And the way to think about this is that most of the jump operators, all the jump operators except for one, are multiplied by some small coefficient, and the one remaining jump operator has a form that's fixed by the requirement that the map be CPTP, and so it's given by this particular form. And so when you plug this in, you find that a quantum channel close to the identity looks like a Lindblad master equation, and this particular special outcome that corresponds to not seeing anything during an infinitesimal time step is described by what's called a non-Hermitian effective Hamiltonian. And so if you post-selection never seeing anything coming out of your system, the conditional evolution is described by this non-Hermitian effective Hamiltonian. And so we're going to talk about what happens when, can this guy have phase transitions or not? And so the simplest case where I can show you something interesting happening is that of a two-level system. So two-level system, you sort of measure the y component, and it's easy to check that that the no jump evolution is governed by this effective Hamiltonian that's got a factor of 1 plus sigma y in it. And now if you write this out, then the effective Hamiltonian turns out to be completely real because I times sigma y consists of real numbers. And there's this part proportionally identity which has no dynamical significance. It just corresponds to the fact that I'm continuously losing norm as I time evolve. And so this is a real matrix, and so its eigenvalues come in complex conjugate pairs. And in fact, you find that there is a transition in the structure of the eigenvalues of this matrix as I crank up the rate of measurements. And so this transition is well understood in the non-Hermitian physics community. It corresponds to an exceptional point at which the matrix becomes non-diagonalizable. And the key thing from our perspective is that there's actually a purification transition, or you can think about this as sort of the simplest kind of purification transition that exists, because when B is bigger than 1, the eigenvalues have different imaginary parts, and that corresponds to different decay rates. So if I evolve for a long time, the only thing that remains is the eigenvalue that's decaying slower. And so that corresponds to purification. No matter what initial state I take, eventually it's going to get projected onto the eigenvector that's decaying slower. On the other hand, if B is less than 1, then both of my eigenvalues have the same decay rate. And so if I take an initially mixed state, it stays mixed at all times. It never purifies. And so this transition is sort of the simplest version of a purification transition. And so it already has a couple of interesting features. The first is you could ask what happens in this mixed phase, where where the two eigenvalues have the same decay rate. And so you could say, well, does an initially fully mixed state remain mixed for all times? The answer is no, it doesn't. It actually partly purifies, and the reason it purifies is sort of amusing. It's because you start out with eigenvectors that are orthogonal, but in fact the eigenvectors of this non-Hermitian matrix are not orthogonal. In fact, they become closer and closer to parallel as I approach the transition. And so if I evolve for a long time, I push whatever initial state I had into a state that's sort of a generic superposition of these two eigenvectors. And so points that are sort of far away from where the two eigenvectors are get sort of pushed into this cone that's spanned by the two eigenvectors. So as the eigenvectors get squashed closer and closer together, what you find is that the purity actually gradually increases because the density matrix is squashed into smaller and smaller part of the Hilbert space. And so the purity actually evolves continuously, and it goes to 1 at the exceptional point. At the exceptional point, it decays as a power law. So in some sense, this looks like an actual critical point, though of course it's just happening in a two-level system. Anyway, so that's a two-level system, and you ask, well, does any of this extend to many body systems? And in fact, if you take a chaotic, generic chaotic model like the Ising Hamiltonian with a transverse and longitudinal field, and you apply the same kind of post-selection, you find that there is a very similar transition that happens. And in fact, you can describe it quite well by performing a mean field decoupling of the interaction and then treating it as a sort of self-consistent ensemble of two-level systems. You can see that this doesn't actually do a great job quantitatively, and that's good because it means the actual physics is somewhat more subtle than the two-level system picture would predict. But again, I'm doing mean field theory in one dimension, so I don't expect it to work so well. There's also a solvable line where you can establish that this really is, that the spectrum really is exactly, everything, all eigenvalues have the same imaginary part. So, so this is not just not effect of bad numerics or whatever. Okay, so the good news is that there is this transition. We know it exists. The bad news is that so far to study it, we've been stuck on exact idealization style system sizes, and these are sort of unfortunately small because the matrix is non-Hermitian, and so that makes all your numerical algorithms work a lot worse. So you're stuck on system sizes of order 12 or 14. But in spite of that, you can see a few interesting structures already. The first is, okay, you have this evolution of purity. It develops these strong oscillations as you approach the transition, and the oscillation period becomes longer. That's some kind of critical slowing down, I guess. Then the other thing to note is that because in the mixed phase, you know what the eigenvectors are, you can go into diagonal ensemble and by performing a time average of density matrix over time. And so this, you can ask about the properties of the steady state, this mixed steady state density matrix, and you can see that its entropies decrease continuously towards the transition, and so there's sort of a non-trivial evolution of its entanglement spectrum. Finally, you might ask, well, is this purification transition also an entanglement transition? And again, we can't say anything very definitive on the volume law side, but certainly certainly the pure phase we can establish as an area law phase. And so we think the mixed phase is the volume law phase. I mean, that's what our evidence says, but again, we're limited to fairly small system sizes. Anyway, so this is a curious example of an entanglement transition where you can actually do spectral analysis, and so we have this nice understanding of it in terms of mean field theory. And so you might ask, well, what does this have to do with experiments? Do you really want to post-select on not seeing any photons for a really long time? And so this raises the question of how do you actually study measurement transitions? And the best idea we have so far is the thing Matteo is going to talk about tomorrow, which is to use space-time duality to relate these transitions to looking at unitary circuits sideways. And so, this raises the interesting question of, are there unitary circuits that have this property when looked at sideways, that are described by PT symmetric Hamiltonians? And so this is an interesting challenge to come up with. I don't see any reason why there shouldn't be, but in that case, you could ask, what is a PT symmetry breaking transition, this purification transition mean in that context? Okay, so that's all I wanted to say about the case with time translation invariance. Now let me very quickly talk about the case with U1 symmetry. So in this case, what's the model we're talking about? We're talking about a model of qubits coupled to, let's say, some large D qubit. And so the qubit has a conserved charge, but the large D qubit is around just to make the Hilbert space big. And then so, U1 conservation forces this block diagonal structure for your gates. And so, these blocks are individually taken to be in a tractable limit. They're taken to be large, so you can perform averages over them efficiently. And then, okay, if you have the structure, you can perform a mapping to stat-mech model, which I won't have the time to really describe. But the thing that comes out of this is that you actually, it turns out, have two transitions in two different volume law phases in the presence of the U1 symmetry. So as the original entanglement transition, which we all know, which happens when the system purifies, or when you go from having a lot of entanglement to having no entanglement. But well before that, there's this new transition that we see, that's the charge sharpening transition. And so that's what I want to talk about very briefly. How do you detect this charge sharpening transition? You detect it by looking at the variance of charge on a single trajectory and then averaging that over trajectories. Remember that the variance is not a linear function, and unlike an expectation value, and therefore the variance is a thing that cares not about the channel, but about the decomposition of the channel into trajectories. And that comes entirely from this bit that sort of, you square the expectation value and then you average it. So that makes it nonlinear. And so this variance, in fact, shows a nice crossing at some value of the measurement probability. So you could ask, what's going on here? Why is the variance growing with system size on one side and not growing system size on the other side? So let me talk about, so in some sense, what happens over here in the sharp phase is simple. What's happening is basically you're performing your measurements. The measurements are figuring out what the local charge density is, and so they're collapsing the global charge into stuff that's sort of locally sharp. So the measurement's just figuring out what the charge is quickly, and that's the end of that. What happens at small values, at small measurement probability, though? So here's a quick discussion of how this works. So let's say that you have measurements every now and then of what the charge is on a particular site, and then you let the system scramble and you measure the charge again, and then you let it scramble and you measure again. So it's like you're getting a bunch of independent samples of the charge density, and what you want to ask is how many samples do you need in order to specify the charge, in order to know what the charge is down to an uncertainty of order 1. And if you've ever done error analysis, you'll know the number of measurements required to get that accuracy is L squared. And so how long does it take you to accumulate L squared measurements? Well, you're performing P times, that's the probability of measurement times time measurements at every time step. Yeah, so you're measuring P times L qubits at every time step. You do that over and over again every time step, and so you get a factor of T from that. And so what you find from this estimate is that when P times L times T is of order L squared, so for times of order L, you break down the measurement uncertainty down to like some number of order 1, and so that corresponds to extracting what the global charge is. So in fact, that is consistent with what we see numerically by sort of time evolving the transfer matrix of the StatMech model. Okay, you could ask, in addition to that, suppose I go to my late time steady state, what are the local fluctuations of charge? I don't just care about the global charge, I care about what the local fluctuations are. And rather surprisingly, we find the local fluctuations of charge are those you'd expect for a Luttinger liquid. And so, in fact, even though the system is in a volume law phase, the charge sector decouples and is described by Luttinger liquid physics. And so, as you crank up the measurement rate, you find that the charge variance is a coefficient. This coefficient goes down. When this coefficient hits a critical value, you undergo a Kosterlitz-Towless transition into the charge sharp phase, which so in some sense, if you know the superfluid to insulator transition, the charge fuzzy phase looks like a superfluid, the charge sharp phase looks like an insulator, and there's a KT transition between them. And so we have now fairly strong numerical evidence that that's what happens, and it happens somewhere over here. So it's, as you might expect, slightly lower measurement probability than the previous numerics was extracting. Okay, you could ask, is this specific to large D circuits? In fact, we find that this sharpening transition happens before the entanglement transition, even for qubit chains, and so it looks like the existence of these two transitions is fairly generic. Okay, so that's most of what I want to talk about. So we have these two transitions. The charge sharpening transition is a new feature, and so we'd like to find some models where we can solve where we can understand this in a more tractable way, and so, maybe duality is good. Unfortunately, charge dynamics is trivial in Clifford circuits, so Clifford circuits don't help us. Okay, so I think that's basically all I wanted to talk about today. You have this purification transition that we've been talking about in random circuits, turns out to have a much simpler analog even in two-level systems, and more generally in chaotic time invariant circuits. And then once you put in additional structure, what you find is there is still a volume law phase, but within the volume law phase, there can be these new transitions that we're still just beginning to understand. And so that's I think the extent of my talk. So thank you for listening.
Thank you, Sarang. Yeah, so we are now open for questions.
Sarang, can I ask about whether there has been any studies about local entanglement in the sense of, let's say, concurrence or something like that? Because it would appear to me, so your measurements are happening at individual qubit levels, right?
Yeah, that's right.
So, so there's this early things about persistence of entanglement, and there are certain states which are more persistent and so on. I mean, that's how the graph states are constructed. So my question then has two parts. I mean, how specific it is to these kind of states, matrix product or graph states, and versus what happens to local entanglement in these?
So I think that, I mean, in some sense, yeah, so if you ask about sort of the smallest, so the simplest non-trivial kind of local entanglement that people have looked at is something like, first of all, let's say you could talk about the mutual information between two qubits that are separated by some distance. You can also ask about other properties of those reduced density matrices, like the log negativity. And so people have looked at those observables, and they sort of pick up more or less the same aspects of transition so far as we've been picking up using the simple-minded entanglement entropies. But yeah, I mean, there's a lot more to be asked about this, and I think, and quite recently, Ehud Altman had a paper saying that that the log negativity is robust against the addition of sort of local mixing at the boundary. So in that sense, it might be a more robust probe that would be interesting to look at. But yeah, not very much is known, in short.
And about the states themselves, I mean,
what do you mean exactly?
Yeah, I mean so in these things, you are looking at a time evolving state, and then you're doing also measurements, correct?
Yeah.
So okay, so I guess then it's well, it's a question of then the difference between, let's say, something like a simple Ising model without, I mean, an integrable Ising model versus something which is not. So how would you characterize that?
All of this stuff is in the chaotic regime. That all the most interesting consequences are in the chaotic regime. So they're in a regime where whatever initial state you start with, in the sort of non-trivial volume law phase, they become highly entangled, and they're sort of not, there's not efficient. As far as I know, there is no efficient representation of these states.
You could have even something like a transverse field Ising model kicked, let's say, and that's going to still produce. I mean, that's probably well, that's still going to be a highly entangled state, although
so,
it's.
In the presence of measurements, there's not, right? I mean, the point is the measurements are very effective at removing entanglement
Okay,
from Gaussian states.
All right.
So the fact the state is, so the key thing here is that, you might expect, very naively you'd expect, and this is what the first paper talking about this said, you're performing measurements, that's removing entanglement at bulk rate. You don't need growing entanglement in the boundary. So you expect the measurements to always win in some naive sense. And in fact, in integral models, that is what happens. The reason why chaos breaks that is that in chaotic systems, your operators become extremely complicated very fast. So it becomes impossible for measurements to extract local information about them. So it really, the fact that the state survives the measurements is related to the fact the state is extremely complicated.
Okay, interesting, thanks.
So Sarang, what about weak continuous measurements?
So that was the case that I took an extreme case of weak continuous measurements when I was talking about post-selection, right? So this entire thing was, in some sense, weak continuous measurements, whereas post-selecting on a single trajectory. And so here I guess this is what the answer is. There is a transition. If you take weak continuous measurements where you let the outcomes be random, so you do include jumps, and you look at random trajectories, that I believe also has a phase transition, which is in the same universality class as the regular random circuit transition.
I see.
So it seems not to very much matter if you're performing strong measurements, randomly every now and then, or you're performing weak continuous measurements all the time. Those seem to look the same.
Right, but one extreme of weak measurements is no measurements, right? So the
but that limit you have to go to infinitely late times, right? So if you scale time appropriately, there is that limit. But yeah, so if you perform really weak measurements, then it's like decreasing the probability of measurement by a lot.
Right.
Any finite probability is somewhere in this phase diagram. It's not a different phase diagram.
Okay. All right. Anyone else?
Can I ask a question?
Sure.
Not a question, but it was just a curiosity. So in these measurement-induced transitions, so if I think like, the prequel construction, which was discussed in the earlier works also, earlier talks also. So there is a sort of the unitary evolution in general tries to entangle different subsystems and all, and the measurements sort of disentangle things. So what is the role of the entangling property of the individual block in terms of these transitions? Like, does it depend on if the sites are entangled with a more entangling gate or less entangling gate, like a swap gate, for example, and some extreme gate?
Yeah, no, that's a great question. So I think this is in part. We know, I can tell you some things about this, right? So obviously, if you apply swap gates, you're not going to have an entanglement transition. You're never going to develop entanglement, right? But in general, so what we know is that things that are free fermion-like don't make operators complicated enough. It seems more important, the entangling property is the operator scrambling property. So it's really the scrambling nature of the gates that seems to be important. And so the basic intuition that I have for this is, and so this is based on this paper that we did with Matteo on. So what happens is that if you apply a measurement here and some evolution here, and then another measurement up there, it's sort of like time evolving your lower projector to your upper time. And so your lower projector becomes some complicated operator because of scrambling gates. And so what effectively happens, the volume law phase, is because of scrambling, any two consecutive measurements don't commute with each other. So it's like you're measuring the X spin and then you're measuring the Z spin. And that's useless because your second measurement's throwing out all the information that you acquired from your first measurement. And that's why you're not actually extracting information from the system, because it's like you're continuously performing measurements that don't commute with each other. And so and because they don't commute, they're not picking up new information, and it's the measurements themselves just sort of randomizing your state as they acquire information. That's a rough intuition for what you need to have happen. And so to make this happen, what's the commutator between your earlier operator and your later operator? That's given by the OTOC. And so that's the connection between sort of what you want the OTOC to do and what the measurement-induced transition cares about. So you have a time evolution where the OTOC is simple, then you're not going to have a measurement-induced transition because your operators aren't getting complicated enough. Your OTOC's not filling in enough.
So, for example, if I consider this special dual unitary models where OTOCs can be written in terms of, so you think that there won't be measurement-induced transition?
Oh, no, there will be, because, so we actually have looked into this. So, and it turns out dual unitary circuits do have measurement transitions that are scrambling. The OTOC is not simple, right? The OTOC is actually quite complicated. The OTOC fills in the entire light cone. The correlation functions are simple, but the OTOC is very complicated. It's sort of, it's maximally chaotic. So those do have a measurement transition. In fact, those are actually nice models because the measurement transition has some like symmetry properties that allow you to extract some critical exponents more accurately. So that's something I didn't talk about today, but that's something we have looked at.
Yeah, it's somewhat related to this simplification of OTOC. So in the dual unitary models, there are like two extremes. Two extremes are like swap, and there is other one, just like the sort of apex of this dual unitary models is the Bernoulli circuits or two unitaries, which, Carol, I don't know whether you were here in the morning. Those are called two unitary operators, and they're simple in the sense that not only they remain unitary with respect to realignment, that means sideways contraction is unitary, but also with respect to partial transpose. So I was thinking if one uses those, those are like quite, they don't first exist for qubits, they exist for qubits, for q equal to 3 case. So I was thinking if those are taken as building blocks of the models, then maybe the OTOC can simplify and one can look into, because that's like maximally entangling case also. And I have heard in some of
I agree, yes. So the question is not like, is the OTOC simple or not, right? The question is the OTOC occupying a lot of space?
Okay.
So on the swap gate, the OTOC doesn't occupy a lot of space, it just sort of moves along the light cone. Another simple thing that can happen is the OTOC just completely solidly fills in the triangle. And those are both simple, but one of them is sort of very good for, the latter one is very good for entanglement transitions, and the former one is bad. Right, so it really, but I mean, the question you raised is an interesting one. I think it's worth exploring.
Yeah, because I heard one talk by David Hughes where he talks about you have also make some correction to 2D population problems and all. And the point which he said kind of initiated this curiosity to me. He said that when this dimensionality is large and all that, everything is maximally entangling. They can just make that cut and all that. So maximally entangling, then I thought maybe Q equal to 3 is large enough dimension to have maximally entangling gates in the form of these Bernoulli circuits and all. Maybe.
No, I think that's right. I think that, I mean, there are all these perfect tensors and things like that.
Exactly,
as well.
exactly.
So, I mean, I think, so, I mean, in some sense, there are, so I think that, that from the perspective of, from the perspective of this transition, I think that anything that fills in the light cone is good. That's the thing that actually matters. So I mean, even a Clifford circuit, which doesn't really become very complicated, right? It just becomes some kind of random Pauli string. Even a Clifford circuit is good. So in that sense, I think this is not like super demanding. You can get this transition even if you have many body localized quantum circuits, and so it's really not very demanding in terms of what the entanglement properties of gates are. Just need to be like enough. Just need to be entangling enough to make complicated operators. Where complicated operators means they need to be random operators that have support at least 4.
Okay, thank you.
I think we have another question from somewhere, right? I saw a hand raised.
I think it was me only.
Oh, really?
Yeah, I think it was me.
Thank you.
Okay, with that, I thank Sarang once again and thank all the speakers of the session.
Sorry, Vaibhav, actually, I think there's a hand raised from Ranjit.
Oh, okay.
Is there a time?
Yeah, please go ahead.
Okay, sorry, I probably missed it. when you introduced the non-Hermitian Hamiltonians, you have unshared the screen. Okay. So
It's fine, I can share it again if I have to.
did you introduce them as a sort of approximation to the Lindbladian you showed in the previous slide?
No, they're not an approximation. So they're a particular trajectory. In particular,
okay, you are selecting
where...
trajectories in which a jump is not there, right?
Correct. Yeah, that's right. So it's so we're talking about quantum phase transitions in trajectories, right? And so I chose this as a particular trajectory that I could describe exactly.
Okay, so so that is the sense in which measurement is entering into this non-Hermitian.
Yeah, correct.
Because it's not really non-Hermitian system, but an open quantum system evolving according to this Lindbladian actually.
Yeah, exactly. It evolves according to Lindblad, but what you're doing is you're post-selecting or not seeing any jumps, and that gives, and the conditional evolution is a non-Hermitian Hamiltonian.
Okay, so in such an evolution, you talked about this purification transition. If I understood correct, this purification transition was happening around exactly this PT symmetry breaking transition.
Yeah, it corresponds to the PT symmetry breaking transition. Those are the same thing.
Okay, somewhere you talked about ignoring a term proportional to identity, which corresponds to overall loss. So I was wondering what would be the total amount of loss at this phase transition point?
It just, I mean, so it's some non-universal quantity, right? I mean, because the total, so if you start out, there's this coefficient gamma, and there's a term that's like gamma times the identity. And if you have a system of L spins, then it's L times gamma, you know, because you've got to add up all those pieces that proportional to the identity. So the norm of the state is getting lost at a pretty fast rate. I mean, that's true of all these measurement transitions. You're losing norm very fast. And then there's some coefficient, that's the critical gamma, which in this case is 1. Actually, it's not 1. It sort of depends on where you are on this phase diagram. But yeah, so there's no, so the value of the loss at the critical point is non-universal.
I'm asking this question because I was wondering if this phase transition is really accessible. I mean, in some kind of experimental open quantum system.
I mean, not for a big system, but that's true of all of these measurement-based transitions, right? I mean, so for example, in the state of the art in trying to realize these things is you can do it for 6 qubits. And for 6 qubits, you can certainly do this as well. I mean, all of these things are a bit abstract because they're not, you know, yeah. I mean, if you can't generate the post-selected trajectories efficiently, you can't do this efficiently. I mean, the hope is that somehow there are crossovers associated with these transitions that'll survive even if your post-selection is only partial, and that makes it less demanding. But that's not really understood yet.
Okay, I mean, are you aware of any experimental implementation of this already? I mean, in the sense in open quantum systems.
Well, so there's the measurement transition got experimentally studied by Chris Monroe's group using ion traps. So it was like for a small number of qubits you can do it, but it's hard. It's a difficult experiment even for 5 or 6 qubits.
Okay, thank you. That's all of the question. Thank you.
Okay, thank you, Sarang, once again.
Right.
Yeah. So, thanks, Vaibhav. Thanks for sharing this session. And I would like to thank all the 3 speakers of this session, and also Vaibhav Modak for sharing this wonderful session. Thank you all. And we are closing this session, and we will be meeting tomorrow at 2:30 p.m. of Indian Standard Time. So thank you all the participants who are actively participating. We are very thankful for your participation. Thank you very much.
Bye.
Bye. Thank you, everyone.
Bye.
You too.